Hello all of you. Welcome to the 13th lecture on the course on analysis and modeling in chemical engineering. In this lecture, I will start on the idea of representing a process and the idea of flow sheeting. In the previous lecture and the lectures before that, we have already discussed the fundamental laws and concepts in chemical engineering. But now I will kind of zoom out a bit and look at this chemical plant on its entirety before we zoom down again to like smaller scale systems. So what I mean by here is that, of course, I mean, one can start from the molecular level where a chemical reaction takes place. Let us say a catalyst surface, right? That is the maybe the lowest level of representation that is important to us for a chemical engineer, because we want to design catalysts that can facilitate the reaction between the reactants, right? Maybe if we want to make the porous catalysts, then we are interested in having high surface area so that reactants can go inside and react and things like that. These are happening in a very microscopic world, so as to speak, where chemical reactions begin. And as chemical engineers, we want to perform chemical reactions. But I want to zoom out from here and let's say look at a process unit where the same reaction is happening at a much larger length scales, right? So, want to produce tons of that product using tons of reactant and maybe more, using probably a large quantity of catalysts and so on, right? So, that is a zoomed out representation. We are looking at a process unit that is, I would say, tens and fifties of meters as compared to maybe of the something of the order of a nanometer, very small length scale and similar time scales, right? And then from the unit we can further zoom out, and now we are looking at a process plant that integrates multiple units. There is energy integrations, there are process integrations and things like that, and we can keep on zooming out and out, and we will look at the plant as a whole. Maybe we can look at a sector containing all those plants. Let us say you will have so many steel plants in India, then you want to look at all of them together, or oil refineries together. And then finally, we can also zoom out further and look at the level of a country, that what kind of chemical industry is there and what is coming in and what is going out and things like that, right? So what we want to understand as chemical engineers is pretty much these diversity of the length and time scales and things like that, right? As chemical engineers, we want to know what India as a country is producing, or maybe what is being produced in the globe, then what are the companies in that sector, what is the production capacities on those, because that determines my supply chain. Where will I get my raw materials, who will buy my products and things like that, right? But within that sector you will have those plants, and in this plant I am producing still a large diversity of chemicals, and within that plant I will may have certain process units that already is a combination of many equipments, and that basically tells me like, okay, this is being used to produce this chemical, but it includes things, many things more than the chemical reactor. In fact, chemical reactor is only a small part of the story where reactions take place. That's the heart of the story, but it's still a small part of the story. And then finally we can narrow it down to a chemical reactor. In the next week we will start talking about the modeling of chemical reactors, but we need to understand this diversity of scales, and we want to model processes, we want to model systems across all these kind of scales, right? That's the hierarchy that we should keep in mind. So then if I now look at, let's say, a process plant, and somebody wants to put money to make something, what does that depend on, right? Let's say I want to make money to build a new facility to manufacture ethanol. In that case, the very first thing that will come here is starting from a scale that is right here. What is the ethanol demand in the country and how it is being met at the level of the country? How this particular sector is doing before even deciding to consider any process to make ethanol or any chemical for that matter, we need to start from this perspective, starting from the globe or at least India, right? And then only we can have a reasoning that we need this particular process. But once we have done that, then we will start looking at the chemical process that will be required to make or produce that chemical at a large scale. Once we are formulating this idea, we do not know all the details, whether we use a CST or a PFR, whether we do distillation or an absorption, whether we do some kind of a reactor that is cylindrical versus some kind of a distillation column or a tank that is rectangular, right? I mean, of course, we go for mostly cylindrical ones, but just an example of the idea, right? So we don't want to discuss about those details. Those details are very, very important, but yet at the basic stage of conceptualizing a plant, we don't need that, right? So those kind of diagrams that we build at that stage is what is known as a block flow diagram, right? Where we have a need, we want to produce ethanol, let us say from some feedstock that we have from agricultural stuff, and I want to convert that into ethanol. That is my overall goal. And what are the essential steps that has to be performed to get there at the level of the process? I want a reaction, I want some separation, I may have to do some preheating, so on and so forth. At least those basic physics need to get there. So when I'm doing this kind of a diagram that contains basically a simple overview of what is going on, and I'm representing processes mostly as like blocks like this, because I don't even know what exact kind of an equipment I will use in there, and just simple arrows to demonstrate that how things are flowing in the plant, just a basic thing. Of course, it has to be improvised quite a bit before it can become a reality. That diagram is known as a block flow diagram. Of course, I can do the reverse. If let us say you go to a chemical plant as maybe a summer intern and you want to figure out what is going on in the plant. Of course, there are thousands of different units out there, and if you want to kind of get a sense of what is going on, the simplest possible representation one can build are these, again, this block flow diagrams, right? This is the zoomed out representation of what is going on in the plant, and of course I can zoom in then in every unit and see like what is going on in there, right? It's very, very important for us to be mindful of the diversity of the length scale that we have. But at the same time, as I was telling for the previous modeling example, is not to overthink. If we try to look at everything at once, then there are millions of chemical processes, physical processes happening in there, and there is no way we can make our way through chemical plant understanding or anything of that sort, right? So we need to have this kind of a conceptual diagram to begin with if I try to understand a plant, and at the same time, this is something that we also have when we try to basically think about making something in a stage of conceptualization, right? The next level of detail is what is known as a process flow diagram. Okay, so one has figured out that this has to be done and it is convincing idea, there is a demand for this product, I can use this feed, right? More or less this idea appears to be something that is feasible, again that comes from experience. And now I want to work out the details, right? So for example, what kind of columns I can use, how will I do this heat exchange, what kind of reactors I will do, what will I use my heating medium, how will I pump it, right? So I will start thinking about those details now, right? And when that is done, what one gets is a process flow diagram, right? And again, going back to the example when you are visiting as a summer intern, once now you have figured out what is going on in a part of a chemical plant or the overall chemical plant, now you want to focus on the details of that. If it is a small facility, then maybe you can do the process flow diagram of the entire plant, or you can focus on a particular unit of that plant and then see like what exactly are the equipments there. That is now zooming in, looking at the processes in more detail, right? But then there is another level of detail that makes up what is known as a P&ID diagram, which also includes pretty much all the details around each and every equipment out there. Let us say you will have a chemical reactor. So, it will have some temperature measurement system, temperature controls, pressure controls, moisture controls, all those things out there. And in reality, that control circuit, those control loops around it, which are very, very important in order to automatically control the process, but that is really overwhelming, right, for anyone who is looking at it for the first time, right. So, notwithstanding the fact that it is important to have those controls in place, we typically go ahead and work with the process flow diagram to develop initial understanding of the process, but when it has to be commissioned or when it has to go through some kind of maintenance in the actual plant, then one really have to look at all those details as well, right. So, in terms of complexity, we are going from left to right and it becomes more and more complex. This one I will do a lot when I am trying to conceptualize a chemical plant, right, or want to understand the chemical plant. This one would do a lot once that want to look at something in more detail, right, but not really at the level of implementing the idea or doing some modifications. But this one is one that you will do when you want to commission it or to plan any modification around the particular plant. So, we will mostly focus on the block flow diagram, but this idea should be very clear to you. And in fact, when you do a process simulation, mostly you will work with something like process flow diagrams. But in this course, I will mostly focus only on the block flow diagrams, because our focus is also a lot on the modeling of subsystems, let's say chemical reactors, evaporators and things like that, rather than looking at this entire plant as a whole. We will do that partly, but not in more detail, right. So, therefore, one has to keep that picture in mind, and I will show you some examples in this week, but then in the following weeks we will look at particular equipments in more detail. All right. So, this is one example of a block flow diagram, and how does it help me, right. So, let us say for example, if you do not have this diagram in place, what you may have is probably a description of that process, right, and description is given here. What it tells me is toluene and hydrogen are converted in a reactor to produce benzene and methane. The reaction does not go to completion and excess toluene is required. The non-condensable gases are separated and discharged. The benzene product and the unreacted toluene are then separated by distillation. The toluene is then recycled back to the reactor and the benzene removed in the product stream. Now, if I read that and if you do not have this figure with you, it will be difficult for you to fully comprehend what really happened here. In the earlier classes, I have told you how interconnectivity is so important. How will I get an understanding of interconnectivity? We need to draw it out, right. So, let us now read this same description a bit slowly and try to construct whatever diagram I have below in our minds, right. So, what is happening here? So, toluene and hydrogen are converted in a reactor. So, we need a reactor. So, we begin with this. So, I have read until this part. To produce what? To produce benzene and methane. So, there are products coming out of the reactor, which is benzene and methane. Only the red part is what I have drawn so far, right. Right. Of course, I have the full drawing with me, but I am just going with you one step by step to see like what exactly is going on, right. So, toluene and hydrogen is being supplied and benzene and methane is being formed in the reactor, and I have drawn the reactor as a block, right. I do not care what reactor is that. Now, it is said that reaction does not go to completion and excess toluene is required, right. So, excess toluene is required. You can see here I am using 10,000 kilograms per hour and 820 kilograms per hour only of hydrogen. One can compute the number of moles and figure out that the toluene probably is present in excess already, right. Now, we have been given that the reaction does not go to completion. So, the product stream is going to also have toluene and hydrogen. So, it has the desired product benzene and methane, but it also has toluene and hydrogen in the product stream from the reactor. So, something has to be done with that, because I want benzene, I do not want the unreacted things, right. and that's what is explained next. So, the benzene product and the unreacted toluene are then separated by distillation, but before that what I am saying is the non-condensable gases are separated and discharged. So, it goes to a unit first where I separate the non-condensable gases. So, the gas goes out, and gas probably is not very important here. It is not even specified what are those gases, and the liquid phase probably contain the benzene and the unreacted toluene, right. So, toluene was in excess. So, what is hoped is that hydrogen is more or less used up, but there is plenty of toluene left in this stream of mixed liquid. So, now it is being separated by distillation. So, when you distill it, you may get a product. Probably benzene is more volatile here, that is why it is going from top. And then, since the reaction anyway requires excess toluene, and toluene is not our desired product, it is a good idea to probably recycle whatever toluene we have got back to the reactor. So, there are two major equipment here, the reactor and the distillation column. The reactor is what forms benzene, and distillation column is what separates benzene from unreacted toluene, and in between we also have a gas separation to take out the non-condensable gases, that is somewhere in the middle. So, we have 1, 2, 3 main units in the problem, and then there are many streams connecting them, right. So, what is key here is when I did this block flow diagram, I basically was able to identify what are the main units and what are the streams connecting those units or going out or in the process. And this conceptual picture is required in order to do any kind of calculation or at the level of a process flow sheet, at the zoomed out level of a process flow sheet. If I look at a particular reactor, I will write a design equation of that reactor, but if I look at a process flow sheet, I need to have this kind of a conceptual framework before we can do anything. So, for the same process, one can have a process flow diagram like this. Again, you see some toluene and hydrogen is still coming, right, and it is going to some reactor. It is difficult to make out from here what exactly is going on, right. The block flow diagram was much simpler, but what I want you to look at here is not all the details, but the main thing is that I have all these units which are present in the system, and I am also including some utility units. What are the utilities? I have to pump toluene, I have to probably preheat the feed. These were not earlier considered because we were in the stage of conceptualization. So, we considered the major equipment, not the minor utilities. So, all these units are now being considered, and these units have a certain way of numbering. These are my units, they are labeled in a certain way, and they are pretty much everything has been labeled and listed on the top, and there are streams which are with the diamond symbol and with a number on that, right. So, for doing any calculation or any modeling exercise, or even to prepare or manufacture or commission these kind of things, we need the understanding of that units and streams which are present in the process, right. I will not take many examples of process flow diagrams, but just keep this in mind that I need to have both of these in our framework, how many units are there and how different streams are connecting them in what particular way, and we need to provide that information to the computer, and I will talk about how to do that in order to do any kind of calculation or simulation on this entire flow sheet. So, I am taking one more example from a daily life kind of not a chemical plant, just to demonstrate the idea of a block flow diagram, right. I will again read a problem statement which is no longer about the chemical plant, but still it is chemical engineering nonetheless. So, what the problem says is that you are hired by a campus group, lazy undergrads, just a funny name, as a process modeler for their project promoting water reuse in the campus. One component of their project is reusing the grey water, that is dirty water coming from the outlet of the washing machines in flushing the toilets, right. So, water reuse is a big deal, right. So, we do not want to waste the fresh water. Water is a commodity that we want to save. So, therefore, what I am doing, I am proposing that you have like washing machines. Washing machines are throwing away waste, they contain detergents, right? And if it goes in the in the waste stream, detergents are going to cause harm to the water bodies and things like that, right? And the toilets are using plenty of water, so we want to save the water consumption in toilets, and we want to somehow reuse whatever we can do with the the water stream coming from the washing machine, right? And the good thing is that we also have detergent that is kind of there, so it will also probably have some cleaning effect, we hope that, right? So how it is done? So this is achieved by first filtering the heavy dirt particle from the gray water. So the water coming from the washing machine is called gray water. So that water probably will have some large dirt and things like that, because cloth has been cleaned. So whatever dirt from the cloth, if that gets into the toilet, it is no good. So you want to first remove that. That is probably done. That is done here by filtering. So filtering the heavy dirt particle from the gray water, and then the filtered gray water is stored in a storage tank, right? So it is not like washing machine and toilet is being used together, right? So they will have different times of uses. So you will store the gray water into a storage tank, and whenever it is required, it is supplied to the toilet flush tank as needed. And of course, fresh water is supplied to the washing machine, and maybe it will not be enough, because washing machine can only generate so much gray water. That probably is not enough for flushing. So fresh water is also supplied to the flush tank when the storage tank is empty. So we have some backup fresh water supply as well in case the storage tank is empty, right? And whatever is the overflow of the storage tank, that goes to the drain, right? So I want to draw the block flow diagram of this process and list the relevant variables for the units and streams and things like that, right? So the first step is to draw the block flow diagram. How we can draw it? So we have a washing machine. What does the main function of washing machine? It takes dry clothes, it takes detergent, it takes clean water, and it gives away wet and maybe clean clothes, and this is, by the way, dirty clothes, right? That is the main product of the washing machine. And the other byproduct that we want to use is my gray water. So now the gray water is being filtered. So we have a filter. Filter collects that heavy dirt. I am probably discarding it. And then the filtered gray water is going to the storage tank. Now from the storage tank, whenever it is required, it goes to the toilet flush tank. And any overflow of the storage tank can also go to the drain, because it may be that tank will be of certain capacity, the storage tank. So it may be that if there is plenty of supply of filtered gray water, the supply may be, the tank will be full, and then there will be overflow to drain, right? And the toilet flush tank also gets backup fresh water from the tap whenever it is required. And then whatever water is used up in flushing, I am not reusing it again, it is going to the drain, right? This is again an example of drawing a block flow diagram. When I was talking about modeling, the first step I told in modeling is to have a drawing of the system that you are trying to look at, right? So if you don't have the drawing, the very first step is to construct this kind of a thing also for a process that is being specified. Because once I do that, then I can identify what are the main units. In this case, the main units are washing machine, filter, storage tank, and the toilet flush tank, and we can identify all these streams, and then we can perform maybe material balances, energy balances, and we can find things like what is the saving of fresh water by this system. Whatever we are interested in for this particular problem, one can figure out once I have an understanding of like how many streams are there, how it is connected, what properties I have to specify for the stream, what equations I have to solve for each of the units, and things of that sort. Okay. Now, one thing that is also true is that if you look at any flow sheet, it is made up of units and streams. That if you look at in a very abstract fashion, where I want to focus on the connectivity more than the units themselves, is what is known in like mathematics as graphs, right? So I can draw the same system if I disregard the details of that mixer, reactor, separator, and another mixer 1, 2, 3, 4. If I simply call them 1, 2, 3, 4, then if my focus is to figure out what kind of connectivity is there in that system, I don't need to draw even in all this detail. I can draw a simpler drawing like this, which is called a graph, where I have these vertices 1, 2, 3, 4. Units are now referred in graph as vertices, and then there are edges connecting those vertices. And the advantage of doing that is there is a whole apparatus, there is a whole setup of algorithms which are present in graph theory, which I can now use in the analysis of my chemical process flow sheets, right. So, representing a flow sheet as a graph will be advantageous because I can now use any graph theory algorithms. I told you earlier how this idea of analogy helps. This is not quite an analogy, but the idea remains that we have something done for general graphs, which we can also employ for our process flow sheets, which is also a graph in some sense. Okay. So, just to demonstrate this particular idea, let us think about a completely different case, not from chemical engineering, where again I encounter things that look like my process flow sheet. Just to demonstrate the idea that this idea of these graphs are very general and it comes in many contexts. So, there must have been systems, to study those things, and those systems I can now use in chemical engineering applications, right. So, what is being shown here is a metro rail network that is consisting of some M routes. You may have traveled in metro trains, and the network contains different lines, right, and different lines have different stations, and some stations are common between the different lines, right. And let us say, I mean, just to give you an example of a problem is like, let us say I am here at A and I want to go to B. How much time does I need to go from A to B? What is the fastest route to get from there? I can find distances and I can do that, right. And I can probably know the frequency of trains on each of the routes, how frequently the trains are running in, where I can have these connections between the two trains, right. But what I want to demonstrate here is not this particular problem, but think of it as something that also happens in chemical process flow sheets, right. So, just like trains are moving on different tracks here, chemicals are moving in different pipes of a chemical plant, and those are interconnected. So, therefore, let us say for example, you have a toxic product being formed in one of the pipes. Now, let us say I want to figure out how far it can go, how many pipes it can go to. Again, that is a question of interconnectivity, and that interconnectivity is very similar to the interconnectivity that you see here. I can draw a graph for this, and I can use graph theory concepts to do this problem of train networks, and if I can do that, I can do the same thing for a chemical process flow sheet. That is the idea that I wanted to bring home. So, now just to take it further, let me summarize the basic process of a process design. So, whenever you want to design a process, you first decide whether it is going to be a batch process or a continuous process. And then there are essentially three steps that you have to do. One is called synthesis, the second one is analysis, and third one is optimization. In synthesis, what we do is we choose the structure of the flow sheet, what equipments we have and how they are interconnected, and what is the initial value of the input variables, right. So, you have figured out that I want to make this chemical, and now I want to basically build a process for that. So, in that case, this is going to be your first step to identify what are the equipments, what are the interconnections, and what are the input variables that you have there. The next step is going to be process analysis, where now once you have the flow sheet using the ideas used previously, now you can perform calculations on that flow sheet. What are those calculations for? We can do a heat and mass balance to figure out how things are flowing, what kind of thermal requirements are there, Do I need to heat or cool, or are the systems working efficiently or not? And then we need to do a sizing and costing of the equipment. And finally, as I said earlier, safety is one of the most important aspect. So we can also look at how safe our thing is more than being economically feasible, right? And once we have done this kind of an exercise, now we are ready to basically commission that thing. But before we do that, there is an additional step, that is the step of process optimization. Now I know that it is working more or less as intended, but now I want to maximize profit. Now I want to maximize production capacity, let's say. So then I will optimize. I will now play with the variables or model parameters in the problem. And there are two kinds of things that we can do. One is the parameter optimization. I can choose optimal values of the input parameters, let's say the rate at which the feed is coming in, or the temperature or pressure conditions or whatever. And the second is structural optimization. I can also play with the type of equipment and connections we are using. Maybe if we are doing, let's say, a recycle stream, if we find that adding a recycle will help. In the case of toluene example, we have seen that there was a recycle stream because we required toluene in excess, right? In a similar manner, we can decide whether we need a bypass stream or a purge stream, and you may have learned of these concepts. So any of those ideas will come under structural optimization, right? So any process design for a chemical plant that you want to set up, or anybody wants to do it, it needs to have basically these steps there. After deciding on whether it is batch or continuous, one has to go through a part of synthesis, then analysis, and then finally optimization of the process. So in the coming classes, I will discuss also about what exactly goes into a process simulation. There are softwares like Aspen, which is commercially used a lot, and there is also an open source version of it, called a version of a software called DWSIM. And what they essentially do is they basically provide you ways in which you can draw flow sheets and perform calculations on the flow sheet, and essentially do all this synthesis optimization steps whichever I have shown you. So with that, I summarize discussion of today's lecture. So basically, we have discussed how do we represent a chemical process. We discussed about block flow diagrams, process flow diagrams, P&ID diagrams. We took some examples of that, how to construct those diagrams, and then we discussed the steps of a process design. So with that, I stop here. Thank you so much.